we're now going to see how to determine whether two logical expressions are equivalent in a logical sense. So two statements, R and S, are logically equivalent, which is denoted like this, R equals S. Their truth values match up line for line in a truth table. Here's an example. We want to prove or disprove. Does this statement, is it logically equivalent to this statement? So we have two variables, P and Q, so we put them down. Now we're going to have to figure out the values, the results for this and the results for this. We'll do it in one big table. So in order to figure out the results for this, we first need to do what's in parentheses. So we'll do that. Then we can find out the results for not P and Q. And now to do this, to find the results for this, we have to first find the results for not P and the results for not Q, and then we can put them together with OR. So as usual, we're going to have 4 rows since we have 2 variables. So we put down the values for Q, alternating true and false, and then for P, in groups of 2. Okay, now we're going to do we're just going to go through the columns one by one. So P and Q, not P and Q, not P, not Q, and finally not P or not Q. Okay, now I've bolded these 2 columns, which are the final results for each of the 2 statements that we're trying to think about. So the columns in bold show that not P and Q is logically equivalent to not P or not Q. And that's because they match up line for line, right? This is false, so is this. This is true here, this is true here. This is true here, and so is this. This is true here, and so is this. So since they match up line for line in the truth table, they are logically equivalent. So again, this statement is logically equivalent to this statement. By the way, this rule that we just came up with, right? This rule here, this equivalence, has a special name. It's called De Morgan's law. We'll see it a little soon. Another example, prove or disprove this. So in other words, is this statement not P XOR Q or R? Is that logically equivalent to P and Q, or if P then R? So we're going to make a truth table. We have 3 variables here, P, Q, and R. We are going to have to, well, we're going to have to figure out, we're going to have to find the final results for each of these. First, we'll have to do P XOR Q. Then we can do not P XOR Q. And then we can do not P XOR Q or R. And then for this statement, we first have to do P and Q. And then we have to do P and R. Sorry, if P then R. And then finally, we put them together with OR. Okay, so now we put down the combinations of true and false for P, Q, and R. So we start with R, right, the rightmost of the 3. We put down alternating true and false. Then we do alternating groups of 2, and then alternating groups of 4. Now we do P XOR Q, and now we do not P XOR Q. And now we do not P XOR Q or R. Okay, so we did the first half, right? So we figured out the truth values for this statement. Now we go on to the next one. So we start with P and Q. If P, then R. And then we combine the 2 previous ones together with OR. And we get this. Now we compare these columns that are in bold. They seem to line up pretty closely, except that we see here they don't quite line up, right? So here for this third to last row, they don't match. So since the columns in bold do not match up perfectly, we can conclude that this statement is not logically equivalent to this statement. So we have disproven the original claim, right? We had a claim here that they're equal. We were asked to prove or disprove it. we have now disproved that original claim. Now, there are some important logical equivalences that are used frequently. These are, rules about logic, rules about what things are equal to what things that are equal to other things. So contrapositive law, this is a very important one. We will use it a lot next week. So it says the following. If I have something like if P then Q, that is equivalent to if not Q, then not P. How do we prove this? Answered using a truth table. So this is a good exercise. Prove the contrapositive law using a truth table. It's the same. It's going to be the same procedure as we used, in the first example in this video. Make a truth table. Show that the results of this match up with the results of this statement, and that proves that the two statements are logically equivalent. Here's here's actually a set of two laws known as De Morgan's laws. The first one says the following: not P and Q is logically equivalent to not P or not Q. So a way to remember it is it's the not. It sort of distributes over the P and Q, right? So it gets applied to the P and it gets applied to the Q, but the and gets inverted into an or. Right? That's just a helpful way to remember it, perhaps. But that's not, that's not the reason that it's true. The reason it's true is because they line up, well, whatever. You can make a truth table to show that they're true. That this, in other words, you can show that this is logically equivalent to this by using a truth table. Here's the other De Morgan's law. Not P or Q is logically equivalent to not P and not Q. Now here are two commutative laws. The first one says that P and Q is logically equivalent to Q and P. This is fairly obvious, right? The order of these P and Q doesn't matter. It's P and Q is the same as Q and P. Now let's compare this with things that we know from algebra of real numbers. So A times B is equal to B times A. That's sort of the same. That's also known as a commutative law. Here's another commutative law. P or Q is logically equivalent to Q or P. Let's compare that to algebra. A plus B is equal to B plus A. Okay, so in many cases, and corresponds to multiplication or is similar in some way to multiplication, and or often corresponds to addition. We see this, by the way, in our discussion of counting, right? If you think back there, and corresponds to multiplication, or sort of, as long as they are mutually exclusive, as long as there's no overlap, corresponds to addition. Anyways, distributive laws. So the first one says that P and Q or R is logically equivalent to P and Q or P and R. So this and here distributes over the or, and that makes it P and Q and P and R, and we put an or in the middle, so that we say the and distributes over the or. Compare this to a similar rule in algebra of real numbers. A times B plus C, right? A times B plus C is logically equivalent, is equal to, right? Is equal to A times B plus A times C. Okay, now here's another distributive law. P or Q and R is logically equivalent to P or Q and P or R. Now contrast this with this. A plus B times C is not equal to A plus B times A plus C. Right, so you can't just assume that they're always going to correspond, because this is not true. It's not true that this equals this. So that's for algebra of real numbers, but for logic, we do have this distributive law. And then here are two associative laws. P and and then in parentheses Q and R, that is logically equivalent to, in parentheses P and Q, and then and R. The idea is that the way I associate things, the way I group things together doesn't matter. As long as they're all ands, right? As long as I'm only dealing with and operators, and, the order, not the order, rather, the grouping, the way I associate things together with parentheses doesn't matter. Compare this with multiplication. A times, and then in parentheses B times C is equal to A times B multiplied by C, right? That's also known as an associative law. And this, we have the same thing for or. P or, and then in parentheses Q or R is logically equivalent to P or Q, and then R or R. And again, compare this to A plus B plus C is equal to A plus B plus C. And remember, all of these laws can be proven, all these logical laws can be proven with truth tables.